Rao Bhim Chapter 8, Eigenvalues. Now this chapter or this topic, eigenvalues, is typically the most abstract and difficult topic in elementary linear algebra courses. Now the way Rao Bhim presents this is of course very typical of Rao Bhim without any motivation, intuition or anything. So I would suggest that before you consult this video, please see my other video which discusses the motivation behind eigenvalues in a somewhat non-mathematical way, how it occurs very naturally in different problems. Now after you see this, you will get some basic idea, and we shall assume in this video that you have those basic ideas. Throughout this chapter, we shall assume that the underlying field is C. So all our numbers are complex numbers, so real numbers are a special case. So from the motivational video, you should already know that such equations are of great importance. You often come across equations of this form where someone has given you an n by n matrix over C, of course, and you want to find both V, n by 1, and lambda, a scalar. All these things are complex such that AB equal to lambda V. Now why on earth you are interested in that? We are not going to discuss that here. We will just do the math. For the motivation, you must see those things, that other video. Now just observe that both V as well as lambda being unknown, this is not a linear system of equation because lambda times V, both lambda and V being unknown, does not make it a linear system of equations. So in order to solve this, we naturally want to get rid of either lambda or V. Because if I know V, it is very easy to compute lambda, because all that you have to do, you have to compute AV, and that must be a multiple of V. Just see what is that scalar constant, that is lambda. On the other hand, if someone tells you lambda, it is quite easy to work out V, because you will rewrite this system as A minus lambda I times V equal to 0. Now if you already know lambda, you already know A, so you know this matrix, it is just solving for V. Now I should say that if you take V equal to 0, then of course this is always a solution, so typically people will take V not equal to 0. And any solution to this system of equation will give you two things, V, that is called an eigenvector, and the corresponding scalar, which is called an eigenvalue. Just remember that all these things may be complex. So this may be a complex number and this is a complex vector. Now as I said, if someone gives you an eigenvalue, someone tells you that this is an eigenvalue, then you can directly find out an eigenvector solving this. If someone gives you an eigenvector which is a non-zero vector satisfying this, then you can always work out such a lambda. But the point is, you are neither given this nor given that, both are unknown. How do you attack it? The technique is to eliminate one of them, and for this you write this in this way. Now you observe that A minus lambda I V is equal to 0, and you want V to be a non-zero vector. When is that possible? That is possible only when A minus lambda I is a singular matrix, because if it is non-singular, then a non-zero vector times a non-singular matrix will give you something non-zero. So if this at all has to have a non-zero solution, you must have determinant of A minus lambda I equal to 0. Now this is a great achievement, because I initially started with a system either in this form or in that form where I had got two unknowns, but now I have got rid of one of them. This is an equation only in terms of lambda. And you can convince yourself that if this holds, that we already know, and if that holds, this must hold. So any lambda that will satisfy such a relationship must satisfy this also. On the contrary, if any lambda that satisfies this can be put here, and you can find some non-zero V such that this thing will hold. Because if it is a singular matrix, there must be something in its null space, some non-zero vector in its null space, such that this times this will be equal to 0. So it is enough to solve this system in order to get just lambda, and you already know once I have lambda, I can work out V by solving a linear system of equations. So this motivates definition 8.2.1, which says that I start with any square matrix A, then consider determinant of lambda I minus A. That will be a polynomial in lambda, which I call the characteristic polynomial of A, and I denote it by these complicated things, which is not at all a standard term, standard notation. Now let's quickly understand two things. Number one, just now I talked about A minus lambda I. Why did I switch to lambda I minus A? There is no great reason. In fact, many authors define it to be determinant of A minus lambda I. But remember, the only reason we are caring about this is to check whether this is a singular matrix or non-singular matrix. So even if you switch them around, the singularity or non-singularity will remain the same, so we do not care. But there is one distinct advantage of this, because we typically would focus on the highest order term of this. Now, if you write it in this way, that the highest order term will be lambda to the power n and its coefficient will be 1. But if you write it in that way, then there will be a minus 1 to the power n, which is somewhat irritating. So that is why this form is sometimes preferable. Now let us quickly convince ourselves that this is always going to be a polynomial. So suppose I take this matrix 1, 2, 3, 4, and then I will form this lambda I minus A matrix. So I have lambda lambda only in the diagonal entries, and the entire A is negated. Okay, now when I try to find out the determinant, what will I get? I will have this times this minus this times this, and that is obviously a polynomial of degree 2 in lambda. Also, it will be a monic polynomial, namely the coefficient of the highest power of lambda will be equal to 1. Now, this is only a 2 by 2 example, but for a general case, you can easily see that you will have only lambda terms in the diagonals. Now, what is the determinant? Determinant is basically sum of product of many terms, and in each of those terms, you will have exactly one entry from each row and each column. So, since lambda occurs like this, lambda minus something in only the diagonal entries, you are never going to have anything like 1 over lambda or e to the power lambda, sine lambda or anything. So you will only have lambda, lambda square, lambda cube or lambda free terms. Now there is only one case when you will have n many lambdas, and when you are taking all the diagonal entries, and that will give you lambda to the power n. Remember, our motivation behind defining the characteristic polynomial was to check for which values of lambda this happens to vanish. So I can easily see that my eigenvalues are going to be the roots of this polynomial, or the zeros of this polynomial. So I want to give them a name. Now, Rao Bhim just to make things look more complicated, they have called it by a different name. Now they call it characteristic roots. So just remember, characteristic roots are synonymous with eigenvalues. Now the book continues with lots of properties about characteristic polynomials, some of them moderately useful, some of them just not at all useful, postponing the main argument. So I shall skip those unnecessary or less important results for the time being and directly skip to Theorem 8.3.2. And it says that if A is any matrix and alpha is any complex number, then alpha is an eigenvalue of A if and only if alpha is a root of the characteristic polynomial. So this was Theorem 8.3.2 and sort of settles the question about finding an eigenvalue. You construct the polynomial, find its roots, and you get the eigenvalue. Now we come to the next half of the problem. How do I find eigenvectors corresponding to this eigenvalue? Definition 8.3.4, we start with some eigenvalue of A. So we already know how to find eigenvalues. We have found one. Now we are trying to find out eigenvectors. Now what does that mean? We are trying to find out some vector v non-zero such that AV is equal to alpha v. And that basically means we are looking for some v such that this is equal to 0, or if you want, alpha I minus A times v is equal to 0. So if I consider the set of all such V's, then that clearly forms the null space of A minus alpha I, except that not everything in the null space counts as an eigenvector, because we also have this non-zero restriction. But we can understand one thing, that if I take all the eigenvectors together with the null vector, then I will get a subspace, namely the null space of A minus alpha I, and this subspace is called the eigenspace corresponding to alpha of this matrix A. The eigenspace of A corresponding to alpha is defined as null space of alpha I minus A. It is the set of all eigenvectors of A corresponding to alpha along with the null vector. One case is of special interest. If alpha is equal to 0, in that case you will have null space of minus A, which is same as null space of A. So this is null space of A. So null space of A is the eigenspace of the eigenvector 0 for any matrix A. Now for any eigenvalue, there are two types of multiplicities involved with that. Suppose I have this matrix A and some eigenvalue alpha. In that case, I already know that this will be an eigenvalue if and only if alpha is a root of the characteristic polynomial of A. Now, since alpha is a root, obviously this must be of the form lambda minus alpha to the power some k, together with other factors which I will club together, call it g lambda, and I say that I have taken all the factors involving alpha into one lot, so alpha is not a factor anymore here. I will denote that by writing g alpha is not equal to 0, meaning that I have extracted all my lambda minus alpha together. Then this k is called the geometric multiplicity. For example, if I have lambda minus 1 whole square, lambda minus 2 and lambda plus I, if this is my characteristic polynomial of a matrix, the matrix has to be of order 4 by 4 because it is lambda to the power 4. The degree is 4. So in this case, the geometric multiplicity of 1 will be 2, geometric multiplicity of 2 will be 1, geometric multiplicity of minus I will be 1 as well. I am very sorry, I just made the wrong statement. All throughout I am talking about algebraic multiplicity. I am sorry. So this is the algebraic multiplicity. I am talking about algebraic multiplicity so far. Now coming to geometric multiplicity, I also know that alpha I minus A, null space of that will give me the eigenspace. Now that has a dimension. So if I consider its dimension, this dimension has got to be some number, some positive number. It has to be positive because it cannot be 0, because since alpha is some eigenvalue, so this null space must contain at least one non-null vector. This number is called the geometric multiplicity of the eigenvalue. Now all this may be quite confusing, so what I shall do is I shall give you a simple example. Suppose I work with this matrix A, I want to find out its eigenvalue, so it is very easy to find out its characteristic polynomial, which is just lambda minus 1, lambda minus 1, minus 1, 0, determinant of that. Since it is a nice triangular matrix, so the determinant is product of the diagonal entries, so it is simply lambda minus 1 whole square. So when you set that equal to 0, you immediately see that 1 is the only eigenvalue, and it occurs with algebraic multiplicity 2. So we write algebraic multiplicity am 1 of A is equal to 2. Now let's compute the geometric multiplicity. For this I have to consider the null space of this matrix. Now when I put lambda equal to 1 there, so I will consider null space of 1 minus, so lambda I, that is 1 times I minus A. So if I put lambda equal to 1, I just get null space of 0, minus 1, 0, 0. So what will be the null space of this? That is not difficult to compute. You just multiply this with an arbitrary vector and set that equal to 0, 0. So I want to find out all xy such that this thing is satisfied. Now this equation simply says that minus y is equal to 0 from the first line, and from the second row I get 0 equal to 0, which gives me no information. In other words, everything here must be of the form x comma 0. So I have a restriction on y and x remains completely unrestricted. So the null space consists of every vector of this form. So the null space is basically the x-axis. I can see its dimension is equal to 1. So I can say that the geometric multiplicity of this eigenvalue is equal to 1. Now it may be still quite confusing as to why we are defining these algebraic multiplicities and geometric multiplicities and torturing ourselves. For that, it will help if we have some mathematical insight. We know that linear transformations are important for many things, and linear transformations may be considered as represented by matrices. So you can think that if someone gives you a linear transformation, you immediately get a matrix representation of that, as if there is a magic black box into which you fit the linear transformation and out comes a matrix representing that linear transformation. Now, in order for this magic to work, you have to put something else in it, namely that something else is a basis. So let's clearly understand this. Suppose someone gives me a linear transformation. I will be considering linear transformation from some vector space to itself. So I have some linear transformation A from V to B. I assume that V is a finite dimensional vector space. And I want, suppose its dimension is n, in that case a matrix will be n by n. It's not that if you tell me V, I can immediately give you A uniquely. For that, I have to specify some basis. So some basis B1 dot 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 up to Bn needs to be specified. With respect to this basis, a linear transformation can be represented by a matrix A uniquely. So if you change the linear transformation, the matrix changes. If you change the basis, then also the matrix changes. Now understand that linear transformations are the things that we are really interested in. Matrices are the things that we can write down easily. So it is like looking through a microscope. So this is the eyepiece, what you see through the eyepiece, and this is the actual object. Unfortunately, the relationship between the actual object and what you are using to represent it is influenced by this extraneous thing, choice of basis, which is something like an extraneous arbitrary choice. So even if I change the basis and the matrix changes, I'm not changing the linear transformation. So when I look at properties of different properties of the matrix, I am actually seeing a mixture of properties, some of them properties of the linear transformation and some of them properties of this arbitrarily chosen basis. Naturally, my interest lies in filtering out those properties of the matrix which are influenced only by the linear transformation, irrespective of the choice of the basis. Now, people tried to come up with one such complete list of properties. That is, if two matrices are same with respect to those properties, then they must represent the same linear transformation, possibly with respect to different bases. And that search was a long one, and finally it succeeded, and this entire story of eigenvalues and eigenvectors came up during this search. So people were looking for those properties of the matrix that are properties of the underlying linear transformation. That is, even if you change the basis without changing this, those properties of the matrix will remain invariant, even though the different entries of the matrix themselves change. Now, eigenvalues are one such property. So even if you change the basis, the matrix changes, the eigenvalue will remain the same. Geometric multiplicities and algebraic multiplicities are also similar such properties. So people thought about them because they were trying to look for properties of a matrix which are invariant under the choice of basis. Some other such properties are trace and determinant and rank. So people were trying to grow this list. So we had got rank, a determinant, then eigenvalues, then trace, then algebraic multiplicity and geometric multiplicity. So that is the underlying motivation. Well, enough by way of motivation, let's get back to our original discussion. Now this structure actually motivates some of the results that were given in earlier section of chapter 8, without of course any motivation in the book by Rao Bhim. So let me quickly tell you about those things. Suppose I change the basis, then I know A will change. How will it change? Now there is a very simple relationship by which it will change. Suppose I fix some particular basis and the matrix that I get is A. Now I change the basis to something else. I will get a new matrix. Now that new matrix is related with this matrix by an interesting relationship, namely PA P inverse, where P is some non-singular matrix. And conversely, if you give me any matrix A and any non-singular matrix P, then PA P inverse and A, they both represent the same linear transformation with respect to two different bases. So that is why this operation, PAP inverse, is of great importance in linear algebra, and it is called similarity. So the matrix A is similar to this matrix PAP inverse. That basically means that both these matrices are equivalent in the sense that they can both represent the same linear transformation, possibly with respect to two different bases. Now just now I said that we are interested in those properties of the matrix which are properties of the underlying linear transformation. More mathematically, I am interested in those properties of A which are invariant under similarity transformations. That is, if A has that property, then every matrix similar to that also has that property. So let's quickly check that this is true about determinant. Suppose I take a matrix A and this matrix. What can I say about determinant of P, A, P inverse? Since determinant will split over multiplication of square matrices, it is actually determinant of P. I will write determinant using vertical bars, times determinant of A times determinant of P inverse. Now determinant of P and determinant of P inverse are reciprocals of each other. They will cancel off and I will be left with determinant of A, which means that if I take two matrices that are similar to each other, they must have the same determinant. In terms of this picture, determinant is a property of the linear transformation and not merely of the matrix. Similarly, you can easily check that if I take trace, the same thing holds, because trace of PAP inverse is basically PA, and this P inverse may be brought to this side. That's the property of trace, and P inverse P will cancel off, so I am left with trace of A. So trace is also a property of linear transformation. Now you may have wondered so far that if I take a matrix like this, why are we spending so much time defining this diagonal and why don't we at all care about this diagonal? Now you know the answer. It is not just a whim. Because we are trying to study the underlying linear transformation, if I add these numbers, that is not a property of the linear transform. You can have some A and a similar matrix to A. They will have different values for this diagonal sum, but they must always have the same value for the trace. So this motivates theorem 8.2.6, which says similar matrices have the same characteristic polynomial. So we understand why it is important now, because similar matrices are two different matrices representing possibly the same linear transformation. And they have the same characteristic polynomial is a very powerful thing, because that will imply that they must have the same eigenvalues as well as same algebraic multiplicities. Now the proof is absolutely trivial. I start with some matrix A and some matrix which is similar to that, PAP inverse. Let's see whether its characteristic polynomial eventually turns out to be characteristic polynomial of A. Now this is nothing but determinant of lambda I minus the matrix, which is PAP inverse. Take P and P inverse out common, so you will get P. Now when you take both P and P inverse out, you will see that you are still left with I minus A P inverse. So understand this step carefully. When P and P inverse multiply together, this I will just behave as a transparent wall. P and P inverse meet and they give you I again. Now determinant of this with that, so it is determinant of P times determinant of this times determinant of P inverse. P being a non-singular matrix, determinant of P and determinant of P inverse cancel out, and so you get just determinant of lambda I minus A, and that is indeed the characteristic polynomial of A. So the characteristic polynomial is the same, is invariant under similarity transformation. Immediately we see eigenvalues and algebraic multiplicities are also preserved by similarity transforms. Theorem 8.2.4 is also motivated from the same principle, namely invariance under similarity transform. We have already seen that determinant, trace, they are invariant under similarity transformations. They were known long back before eigenvalues came into picture. Now we see that eigenvalues are also invariant. So the natural question is, does any one of them follow from the other? Turns out that these two things are special consequences of this. So the fact that eigenvalues are invariant is stronger than the fact that these two things are invariant. And this is given by this particular theorem, which says that sum of eigenvalues is equal to trace and product of eigenvalues is equal to determinant. So if eigenvalues are preserved, so must be their sum, so the trace is preserved. If eigenvalues are preserved, so must be their product, so determinant is also preserved. Now, how you prove it? There are various ways of proving it. The book gives you a very simple way of doing it, namely, it just says that look at the characteristic polynomial. In that case, if you just expand this, so characteristic polynomial is factored in terms of the eigenvalues. I am working over C, so I can always completely factor them in terms of linear factors. That is basically why I am insisting that we should work on the complex field C. Now, if I just expand, in that case I know that there will be one coefficient which will be basically given by summation alpha I. And which one is that? That one will be the one where I am picking only one alpha I from each term and lambdas from each term. So whenever I am forming any term, so how do I get the terms? I pick one from each of these factors. Now, in case I want to get summation alpha I, no two alphas are getting multiplied together. This means I am picking the alpha term from one and all the lambda terms from the rest. And that will have just this thing. So it is lambda to the power n minus 1 because I am picking up all the lambda terms. And then the other term is minus alpha I. So this will be the term inside my characteristic polynomial where the power of lambda is n minus 1. I want to conclude that this has got to be the trace. So just remember that this is the determinant of this thing, which is lambda I minus A. So the diagonal entries are like lambda minus AII's and off diagonals are minus AIJ's on both sides. So when shall I get the term lambda to the power n minus 1? When all the lambdas are supplied by the diagonal entries. So lambda to the power n minus 1 means I have chosen n minus 1 of the diagonal entries. Now when I am considering determinant, I am allowing exactly one term from each row and each column. So if I have chosen n minus 1 of the diagonal entries, the only thing that I am forced to choose will be the remaining diagonal entry because all other columns and rows have been crossed out. But I do not have a lambda there, so I must be choosing whatever is there other than lambda. And what is there? So it is like lambda minus AII, so I must have chosen minus AII. So every time I am getting a lambda to the power n minus 1 term, it must have coefficient equal to minus AII, and I am adding them all up, so that thing must be minus lambda to the power n minus 1 summation AII. So I have described the same thing both from the matrix side as well as from the polynomial side, and they must be the same, which basically means that summation alpha I must be the trace of the matrix. Now this argument I have deliberately given you in an intuitive hand waving form, so think about it carefully or read the book. You can see the argument, and very similarly you can prove the determinant, but this time considering the term where all the constants are multiplied together, that is the term which is free of lambda. So from every term in the polynomial you can get one such equality. When you are considering the lambda to the power n minus 1 term, you get this equality. When you are considering the lambda to the power 0 term, that is the constant term, you will similarly get this equality. You can get one such equality from all the terms, but they do not have nicely describable right hand sides.